I'm Robert Gower and I'm studying electronic engineering at the University of Southampton. Today I'm going to talk a bit about the mixer stage of the audio mixer, as well as op-amps and their various uses in real-world applications. So as you already know, the audio will come in through the audio jacks, through the potential divider, through the filtering capacitors to remove any DC offset, and then into the actual op-amp stage, or the bit that does the mixing in the circuit. So an op-amp is a high-gain differential amplifier. So the differential part just means that the output relates to the difference of the inputs. So if one input's at 1 volt and the other input's at 0 volts, then the differential, or the difference between that, will be 1 volt. 1 minus 0 is 1. So without any feedback, an op-amp's output voltage will be equal to the difference between its input voltages times some gain. Now in an op-amp, the gain is normally in the region of 10,000, 100,000, even higher than that sometimes. So if, for instance, you put a millivolt in with 100,000 gain, you'd end up with 100 volts at the output, and in a lot of cases this is unmanageable. So to limit this gain, and thus make the op-amp circuit actually useful, we introduce some feedback with the resistor R3, as you can see in the diagram. Now, the resistor allows some current to flow from the output back into the inverting input, and via some derivation that you can either do yourself or research or look up, you'll find that the gain is now controlled not by the op-amp's gain, which is, as we discussed earlier, very high, but by the ratio of the resistors on the input, so R1 and R2, and the resistor in the feedback loop, R3. More specifically, it's Vout equals R3 over R1 times VPD1 plus R3 over R2 times VPD2, with VPD1 and VPD2 being the outputs of the potential dividers. So we'll start off by showing how a simple op-amp circuit can amplify an input signal. So as you can see on the oscilloscope, we have the blue trace going in at the input and the yellow trace coming out at the output. Now because the amplifier is an inverting amplifier, you'll see that every point on the blue trace, see at the peak here, there'll be a trough at the yellow trace. You could also explain this as saying the signals are completely out of phase with one another. Another useful feature of the circuit is that it acts as a buffer. This ideally means that characteristics such as the source impedance won't affect the rest of the circuit that comes after the amplifier. Now we'll see how the op-amp circuit can actually be used to mix the two input signals coming in from the phone. So now we really start to see the benefit of using an op-amp to mix the signals instead of just a resistor network, because we can maintain the gain throughout the system. With just a resistor network there'd be losses, but with an op-amp we can keep that at that one gain, that unity gain, and while it's not implemented here, we could even add gains. So say a small input from a microphone could then be amplified up to something useful. So op-amps have countless uses in electronics. They're incredibly useful. They can be used to smooth over imperfections in passive components like capacitors and diodes. They can be used in filters, in phase-lock loops, in amplifiers and instrumentation, in power supplies. Pretty much anything you own will have used an op-amp in its design. One such example is an integrator circuit, which is a technique used in analog to digital conversion. So this circuit's very similar to the previous one we looked at, except it has a capacitor in the feedback loop instead of a resistor. So this means that as a voltage comes in on the input, the output will start to rise, but no current will be able to make it back to the input because the capacitor blocks DC current. So what will happen is that the output will start charging the capacitor, and it will charge the capacitor in a very linear fashion in relation to the capacitance and the resistance value. This means that it will integrate any function, which is incredibly useful because such a simple circuit can do such complex maths. So there's currently a constant positive voltage at the input to the integrator, but the capacitor's been shorted out, so there's no voltage at the output. When we remove that short, we'll be adding the capacitor back in and it will start to integrate downwards in a ramp, because if you integrate a constant you get a straight line. So the output voltage will slope down at a constant rate until it hits the supply rail where it can go no further. So you can intuitively see that the larger the input voltage is, the sooner the integrator output will reach a certain level. So if you can measure the time it takes for the output to reach that level, you can now relate between the analog input signal and a digital measurement of time, and thus you have converted an analog signal to a digital one. Various other methods also exist that use this same circuit as part of their architecture. This is just one of the ways that it can be used as an ADC. So that was the audio mixer circuit and op-amps, and hopefully it's shown you how various physics principles can come together to create something very useful in electronics.